on the ibex. The other one was on the ibex side with the interstellar neutral atoms. So I thought maybe just put them all together and try to just try to go through all different types of things that I do here. I've done here, I started here at PhD. This is an interesting plot. I was going through my previous presentations, and I noticed when I defended my thesis proposal in 2017, we were here. This is the solar cycle 24, and this is the year, it was December of 2017, so we were here. And back then, there was an expectation of a decline in solar activity, and there were some speculations that what the next solar cycle would be like, and people said, there has never been a consensus on what it's going to be like in the future solar cycles. There were some groups that said we are going to have a strong next solar cycle, but a lot of, as we will see, a lot of more reliable, more physical models mentioned weaker next solar cycle, more or less on the same level of solar activity with solar cycle 24. And here, how many years? 7 years later, we are with solar cycle 25. We are very close to the maximum, or probably have reached or will reach the maximum in a few months. And as you can see, it's really very much comparable to solar cycle 24. So first, on the IBEX IMAP side, the interstellar medium, I just need to, because I think people here are from all different backgrounds, I need to explain a few terms. So we have the interstellar medium, and in there we have the magnetic field, the interstellar magnetic field, and the interstellar neutral atoms coming towards the heliosphere. Outside that, we have a combination of a plasma and the neutral atoms that keep charge exchanging with one another, but they have a lot of time to thermalize. So they are thermalized, but then after they see the obstacle from the heliosphere, the first one is what we previously thought maybe is about shock, but right now we think it is more probably about wave. This is where we enter the inner helio sheet, and then the next discontinuity is the heliopause, and then after that we reach the termination shock. So this is still interstellar medium in the outer helio sheet. There's still like the interstellar magnetic field is dominant there, and that is where it starts draping around the interstellar, around the heliosphere. And that means the two populations are separating. The ionized ones are deflected with the interstellar magnetic field lines, and the neutral ones enter the heliosphere. However, there is still some charge exchange happening in this area, and that's when there isn't enough time for them to thermalize. So we will have two distinct populations. The ones that don't undergo the charge exchange, they remain the same. We call them primary population because they don't change and they go through the heliosphere. But the ones that undergo charge exchange, that means previous neutrals are going to be ionized and are going to see the interstellar magnetic field and be draped around or deflected around the heliosphere. But the previous protons, they become neutralized. And they can travel all the way through the heliosphere and be observed by IBEX or IMAP. But the thing is, they keep the properties of the plasma. So that means they're much hotter than the primary population, and that they go in all different directions, and they're of course slower. So from there, we want to see how we simulate that after they enter the heliosphere. These ice and atoms, they all have the same bulk speed at the termination shock where they enter the heliosphere. But their energy scales with their mass, and that means they start with the same speed here, and when they reach here also, the speed are like they are faster because the gravity keeps absorbing them. But then for like helium, oxygen, neon, they all have more or less the same speed. But for the hydrogen, that is the exception here. We have a different speed, and that's because hydrogen is affected by radiation pressure. Radiation pressure is the effect of the photons keep kicking out these hydrogen atoms many times as they are on the 20 years or so that they are traveling through the heliosphere to get to 1 AU. They keep kicking hydrogen out, but because photons are going in the radial direction, they keep kicking in all different directions. So that in the radial direction, of course. But then those hydrogen atoms, they get they absorb that photon. They go their electron goes one level up, and then it loses the photon in random direction, and it goes back to its previous state. That means these hydrogen atoms several times get kicked in the radial direction, but every time they emit the photon in a random direction. That means then there's like an accumulative force acting on them in the radial direction. And that force is what slows down the hydrogen. And that means when hydrogen reaches the 1 AU, it's much slower, less energetic, and it means they go a different path. It means if the green is what we see for hydrogen and helium, the red is what we see for hydrogen, and that means we observe ice and hydrogen at later times. This is IBEX. It's actually orbiting around the sun with the Earth as it is orbiting the Earth. And this is what we call in IBEX the sweet spot, where the maximum of hydrogen, oxygen, all of them are observed here. And the reason is because it is in this direction, so it observes it. The satellite is moving, the spacecraft is moving the opposite of ISN flow. That means the relative velocity is the highest, and that means we have more energetic atoms. And it's actually very difficult to observe these atoms because they are low energetic, and this actually helps a lot. We look through the flow and we observe them with more energy, and that means we have a better count rates here than anywhere else. And especially like as we get past this place where we call the observation season or the ISN season, as we pass, the IBEX is gonna look in this direction. So that means it's not looking through the interstellar flow, and that means we are not gonna observe them. So also, this radiation pressure can be, when the sun is the most active, can be actually more stronger than the force of gravity, and that means we are going to have actually a deflected force that actually have the hydrogen atoms diverted outward. Sorry, I meant repulsive force. So given that we have this instrument at 1U that observes these neutral atoms, hydrogen, helium, neon, oxygen. And this has been on the orbit collecting data since 2009. That means over a full solar cycle. That provides an unprecedented scientific opportunity for us. As you can see here, we have the maps of the two energy steps, energy step 2 and 3, and those are where we expect to observe most of the helium. This is important because helium is the least, as you would expect, is the least affected, as it is traveling through the heliosphere, because it doesn't get ionized so easily. That means it gives us a lot of information about the interstellar boundary and the interstellar medium, how we are interacting with that. So we have all these years of data. This is actually from a project that I worked with Hafiz. He provided these maps. And this is going to be a formal data release on IMAP. And but one thing that we should know about IBEX, these maps aren't just helium, they also include hydrogen. These are practically mostly helium, but it also includes hydrogen. Why is that? When these neutral atoms enter the instrument, they to be observed, to be detected, they need to be ionized. So they hit a conversion surface, and they either if they are hydrogen, they pick up an electron, they become H- ions, and they're detected through the rest of the instrument. Or if they are helium, they sputter H- ions from the surface, and they become observed. So that means if they are helium, and if the peak of the helium looks like this at 1AU, that means they sputter H- atoms from that conversion surface. This means those H- ions are going to be less energetic than the parent atom. For the hydrogen, they are converted. They pick up an electron, so they lose less energy, but they're also, as we know, they are less energetic. They are lighter than helium for one reason, and for the second reason, because of the radiation pressure. So we expect hydrogen to be observed here, and we expect helium to be observed here. Of course, you expect to observe more hydrogen because hydrogen is the most abundant in this interstellar medium. But don't forget the effect of the ionization that happens all the way through as they enter the heliosphere to 1AU. These hydrogen atoms are easily charge exchanged through different processes. So that means they actually get heavily depleted. And we expect to observe much higher rates of helium at 1AU and much fainter, smaller hydrogen peak here. Here I can show you where we see hydrogen and how small it is compared to helium. Here we have the map for 2009 energy step 2, and this is 2009 energy step 3. As you can see, we don't expect to see hydrogen in energy step 3. So we don't see any hydrogen here. And you remember I said we expect to observe helium and hydrogen later than other neutrals. So that means this almost faint signal here is the hydrogen. So this whole thing is helium, and this is what we know that is hydrogen. And this is for the year 2009 in energy step 2, we see hydrogen. In energy step 3, we don't see as we expect. But look at 2014, no hydrogen either in energy step 3 and or 2. Again, that's expected because in 2014, we go through a solar maximum. The sun is in its most active phase. That means there's a lot of more photons to charge exchange hydrogen, and Also, the solar wind is density is higher. So all of these more active sun easily deplete all the hydrogen, and that means the ones that reach 1 U are either too low in energy, like below 5 eV or so that IBEX cannot observe them, or they are depleted enough that we don't see a lot of count rates there. So these are some of the challenges, but then with IBEX we have some other challenges that I'm gonna introduce to you, because from that I'm gonna go to IMAP. You know, as we just discussed, energy step 2 rates include the contributions of hydrogen and helium, and it's very difficult to extract them from one another. The IBEX law observational geometry constraints is constrained, as I explained, to the ISN observation season. It's we can't observe them throughout the whole orbit of the Earth or the spacecraft, and that geometry limitation creates actually a degeneracy in the Wilson parameters that is shaped in a form of a tube. What does that mean? So we only observe these ISN atoms in that, in this region. But then that means it's a short, it's a limited time, and we see what are these Wilson parameters. So we talked about the distribution function of ISN atoms in the outer space and how they enter in the heliosphere. These distribution functions, they are associated. Some parameters are associated with them. We have their density, we have their velocity, which entails speed and also the direction, and also we have the temperature. So that means we have, because we are limited to this region, we see that there's almost a functionality between that lambda, that is the inflow longitude, and the other parameters, the temperature and the speed. So you can see different studies throughout the years. They have gone through these calculations. They have tried to use IBEX data to find those parameters, the temperature and the velocity, to better describe what the distribution of neutral atoms is like in the outer space. And what they have reached is something like this. So that means there are a lot of uncertainties in our the parameters that we get from this type of analysis. Also, another problem is that very few studies have been dedicated to oxygen and neon. And again, that's because they're not as abundant as helium. It's very difficult to observe them. Also, there were some difficulties in there were some issues in the IBEX mission that we needed to make some changes. From some year we got no oxygen and neon. I just don't want to go through that, but just know that we only have oxygen and neon data through 2012. So we only have 3 years to analyze that data. So from here, we know the challenges with IBEX, and we go to IMAP law. The IMAP law detector takes its heritage from IBEX law, of course. But then it is designed to track ISN, like IBEX again, ISN atoms and INAS, energetic neutral atoms. We don't want to go through that. And it has several improvements compared to IBEX. What are those improvements? First of all, we have IBEX orbiting the Earth very close to the magnetosphere. In fact, in a good portion of IBEX orbit, it is in the magnetosphere. And that means we really can't use the data for ISN or for INA observations. But IMAP is going to be located at L1. That means we have all our throughout the year to analyze ENAs and IS. It has a programmable energy window. We will discuss that. So those energy steps that we talk about, we can make changes in that. It has better collection capability. We will talk about it, but like it has the collimator field of view is larger, and the conversion surface gives like a better rates. The ESA system gives better rate. All of that. So the whole geometry factor has been raised. That means we have better statistics, and with ISN add-ons, the problem is always with the statistics. We have better processing power, we have improved telemetry, so all of these help the statistics. And also, the most important one with IMAP-Low, which has maybe a big challenge to build, but also a very exciting advancement, is that it is mounted on a moving platform with a pivot angle. So what does that mean? That means, remember I said IBEX is in that phase, the ISM flow is coming in this direction, and only in a region here we have the ISM season. But now we have that pivot platform, and we have that pivot angle, and that means as we are orbiting around the sun, we can use that pivot angle to again face toward the interstellar neutral flow and observe them throughout the whole orbit, throughout the year. Okay, and here is what we see. I'm going to compare what it's like to have that pivot angle. So these stripes, these are our science observation opportunities for each of these atoms. So you can see we have the helium primary and secondary, hydrogen primary and secondary, neon, oxygen, and deuterium. And you can see how, depending on what direction we are looking, that pivot angle, and these are day of year, throughout the year, how these are like, if we are looking at this specific pivot angle, at this time of the year, that means we have that opportunity to make those observations. And with IBEX, it's always 90 degrees. So that 90 degrees means we have this region to make those observations. So that's our ISN window, our ISN observation season. But with IMAP, we can look in all sorts of directions from 60 degrees to 160 degrees. So what are the constraints with that pivot angle? We can only repoint once a day, and the viewing angle cannot exceed 165 degrees, which still isn't too bad. And also for the first year of observations, we have a limitation for our pivot angle to be between 75 and 105 degrees. So it's here. So we want to have the maximum science return. So we need to plan ahead and provide an operations plan to get the best results. For the first 2 years, we have prepared this operations plan. For the first year, based on this limitation, we have decided to, and also remember for the purposes of IMAP-Low, because both scientists from the ISN side and from the ENA side want their data, and for ENA, they prefer 90 degrees because they really don't care what direction to look at, but they want to have a continuous. So that means the 90 degrees is the best for them. We have every other day we switch back to 90 degrees. So for ISN observations, we have every other day. Of course, we take advantage of 90 degrees whenever it's helpful. So every other day, we have on the even days, we have the 90 degree, but then on the odd days, on the ISN days, we have decided to switch between 75 and 105 to, first of all, extend the observation window for as much as we can, but also to have, instead of having all different sorts of looking directions, having a persistent looking direction so that we can provide sky maps. Not exactly sky maps, but reliable maps, both for INA and for ISN, mostly for INAs also. Because we are looking at the 90 degrees, so we have one set of maps in the 90 degrees, but we have two more sets for 75 and 105. For the second year, since we don't have that limitation, but also we still want to be persistent in a direction so that it's not really that crazy complicated with just switching back and forth between all different sorts of looking direction to make it easier to simulate. What we do is we go on the even days that are ISN days, we have decided to go like this. So where we get the maximum science return, 75 degrees, observe helium, hydrogen, and again here, oxygen, neon, helium, hydrogen here, just like that. And then here, as you can see, just helium. We observe just helium here. We see these are indirect ISN atoms, the ones that instead of coming from this direction, they come from this direction, and we observe them like this. So we have all different possibilities to observe ISN atoms, and first of all, we have the advantage of observations throughout the year. That means we can address that parameter correlation too. But also, and these are from our model and UNH simulations. You can see how we have the different days. These are the looking directions according to our plan and the number of days. You can see how at different days we have the possibilities to only have helium and no oxygen, only have the secondary helium and no primary helium, or the days where the primary helium is dominant. So that means the separation between different populations, that was one of the big challenges, is going to be addressed by IMAP-Flow. And here you see the hydrogen. You can see there are days where hydrogen, primary hydrogen or secondary hydrogen is the dominant here, or almost the only thing that is observable is hydrogen. So that separation of populations can be addressed in this way. Also, we can detect ISN neutrals that is not mixed with oxygen. This is based on another model from Wazowski et al.'s work, from the Polish group that worked with us, and you can see how we have the green and the blue are oxygen, and green is oxygen, blue is neon, and you can see we have days that we only have oxygen, or we have days that oxygen is dominant, or we have days that we have comparable peaks. So it also makes it possible to separate oxygen and neon. Also, as I said, we can use the pivot platform to look towards the ISN atoms at all the times of the year. That means the ISN observation opportunities extend to the upwind of the sun, and that's very important because we lose a lot of these ISN atoms through ionization, and most of the ionization occurs closer to the sun. So that means if we are able to look at them in the upwind, that means we will have much better statistics. And also, like for example, for the case of oxygen and neon, it's going to be very instrumental in separating them, because in the upwind, we have, like in the first year, we are, when we are observing only in the downwind, most of the oxygen is ionized, and we only have mostly neons. But then when we are in the upwind, we have more oxygen because it's first more abundant, and also because it hasn't been ionized as much. So oxygen is going to be stronger in the upwind. So that will also be very helpful. So from there, we get to our operations plan and how it gives us best possible science return. This is the first year. This is the second year. You can see these are different. Here is some that easy to see that, but here you can see the red is ENOS, and then we have the same color code black and gray for hydrogen primary and secondary, orange and pink for helium primary and secondary, and blue and green for oxygen and neon. And you can see how we have the days that they are observable based on the pivot angle that you're looking at. You can see how we cover most of the year for ISNS, except for like some less than 10 years, some 60, 70 days in the first year, but then in the second year, we can cover the whole year. That means we will have a lot of data to analyze. And here you can see the orange here shows what we have in the proposal as the requirements. And this is what actually is happening. Like we are required by the proposal to observe 40 days of hydrogen, 60 days of helium, and you can see the number of days is like 357 days or 460 days. This is for the first and second year, the 2 years that we have the operations plan for. So this is all IMAP gives us. How much is left?
8 minutes.
Really?
Yeah.
Sorry.
Sorry.
So I have to go through it really fast. So this is what IMAP gives us. What do we give to IMAP? First, we improve our model before the launch. So that, and we have done most of it. So we used to use a Maxwellian distribution function, but the actual distribution function is far from Maxwellian for some of the populations. Here we have hydrogen primary and secondary for 2 different cases where we consider the angular scattering in the outer helio sheet, and also for helium. And you can see there are the green is the Maxwellian, and there are cases where we are far from a Maxwellian. So our previous model couldn't do that, but I'm not going to go through these, but we have made a modified version of our model that instead of just going to infinity, assuming the infinity is where we have the edge of the heliosphere, instead of that, we go to specific locations for specific values of speed. We can get a distribution function and we can use our code for that. So the problem with hydrogen and helium, you can see contrary to IBEX, and this is another problem. You remember this problem?
You have 10 minutes.
Okay. You have that problem, but also when it comes to hydrogen, the problem is even more complicated. We expect to observe, based on our simulation, we expect to observe higher transfer rates in energy step 2, lower in energy step 1. It's actually the reverse in the observations. What are the reasons? Maybe a poorly known response function of the instrument, the uncertainty in the radiation parameter that we discussed, over subtraction of ice and helium from the hydrogen, and maybe there are some physical aspects that we don't know. We actually went through our model being modified. That means we are trying to address some of those physical effects that wasn't included in the previous model. That over subtraction is addressed by IMAP. We already said that we can address the separation thing. The poorly known response function. This is the hydrogen peak at 1 AU for the value of radiation parameter being 0.89, and this is for 1.1. And the 2 blue curves are the first and second energy steps. You can see how heavily it depends on the radiation value, and how the ratio of energy step 1 to 2 count rates can be easily affected by that. So we need to go through first IBEX response function, and also we need to make sure that we better understand the IMAP response function. So here we try to at least make sure that the count ratio between the two energy steps is increasing as the energy increases. This is what the model predicts, but you can see the actual data points doesn't show a trend at all. That means we really don't know our response function. The next is thinking that maybe those curves, those blue curves that we have, maybe it needs to be multiplied by a factor, maybe it needs to be shifted in the energy, maybe it is more energy, like it addresses higher energies than we expected. We tried that for a specific orbits for IBEX, and it seems like we need to increase, like shift the energy by more than 15 eV, unrealistically high, and then also a significantly large factor to multiply by our center energy to address that ratio. So that's also not the case. So it means bottom line is we don't really know much about our response function when it comes to hydrogen. So how do we address that with IMAP? Making sure that we understand the response function and the geometric factor. This is what we are going through right now with the calibrations. This is the geometric factor. I'm not going to go through that, but the response function includes all different parts of the instrument. The energy, the transmission energy function addresses the ESA. This is the conversion surface. This is the ESA, and then this is the top. So all of these different parts need to be addressed through these values and through the function, and also the collimator. We have a point spread function. That's actually the best known part of our response function, but we try to improve that. And that programmable energy window that I talked about, here you can see how the energy response function is wider when it comes to the other energy response. Energy resolution. Yes, resolution. Variations in the effective radiation parameter. I worked on that for quite a while, and our results actually show that a 20%, 21, 22% increase in the value for the radiation parameter actually addresses that discrepancy. But it's not really easy to work with the intensity when it comes to the hydrogen. How did we do that? We actually, instead of looking at the intensity, we looked at that. You remember I said hydrogen is going to be detected later than other neutrals. When do we have the peak? Based on the peak location, we found that radiation parameter needs to be increased by 20%, and that actually partially addresses that problem. The lunar radiation environment, very fast, sorry. This is the most updated, actually, this is up until a few days ago, the most updated dose rates that we observed with Crater. Crater orbits around the moon. It detects the dose rates of both GCRs, galactic cosmic rays, and SCP solar energetic particles. And it, because I'm focused on the GCR side, so here I have removed the SCPs, and here you can see this is, of course, we expect to have higher rates of GCRs at the solar minimum. So this is the last solar minimum, and lowest values are going to coincide with the solar maximum. And you can see this is the maximum of solar cycle 24, and this is solar cycle 25, almost peak. Here's the sunspot. Thanks. We had this we looked at this correlation between the modulation potential value. Modulation potential value is the energy that GCRs lose as they go through the heliosphere. We found a correlation between this, and it's actually a well-established correlation between the Phi over V, the solar wind speed, and the intensity of the HMF, the heliospheric magnetic field. But when we make this is data, crater data. When we use crater data, instead of just seeing a correlation, we saw some sort of hysteresis kind of behavior. And we actually thought maybe we can look at these hysteresis behavior in the previous cycles. So I did that. I went through solar cycles from 1 to 24, and I saw there are actually trends to sort of predict the next solar cycle. If we have a shape like this, so increase with a steep slope and then, slowly and then steep slope, that means the next solar cycle is gonna be weaker. If it's the other way around, next cycle is gonna be stronger. And if the slope is more or less the same, that means remains inconclusive about the next solar cycle. So we did that kind of analysis. It was very difficult to actually convince referees that this isn't just something we see by eye, and we can actually consider provide some form of machine deciding for us which one it is. But you can see the results. We have actually for more than 85% of the cases, it predicts the next cycle successfully. There's also a correlation between the maximum of the intensity of the heliospheric magnetic field at the solar max and the previous solar minimum intensity coordination. The interesting fact here is that for those cycles, the blue cross shows that. The cycles that we predicted to be weaker mostly are on the lower side of that correlation. And the ones that we predicted to be stronger are on the upper side. So that when we remove, because that correlation exists and is well established, but it's not a very good correlation. But when we include that effect and we only consider the inconclusive cycles, it's actually it gives us a very good correlation with that R ratio to be like 95.95. So based on this, we predict solar cycle 25 is going to be a big solar cycle. Bigger than cycle 24. And that means we should be careful about the planning crewed missions about the GCR radiation. We have previous studies considering previous solar minima. I'm not going to go through that, but this is what we have for the HMF solar wind speed, the modulation potential. This is what we had up until here for our 2020 paper, but for the newer paper that I'm working on, those two minima, Glaisberg and Dalton, you see we are right in between them, but closer to the Glaisberg. And this is the most updated crater data. We had expected to be somewhere between the solar cycle 24 and the Glaisberg, and you see we are right in between. And that, I just, with this plot, wanted to mention that if you look here, these are the permissible mission durations. How long astronauts are allowed to be in a space mission, and you can see how low this value is compared to previous cycles, compared to the time for Apollo and other missions. So this is because the sun is in a lower active phase at this point compared to them. And from here, we reach to the permissible mission duration. When we had our 2020 paper, we had different standards and models for male and female astronauts. And based on that, for cycle 24, these were the values that we had as permissible mission durations, 470 something and 320 for the female astronauts. But this was based on 3% read at 95% confidence level. NASA has actually acquired a new standard that is less limiting. They consider 600 millisievert that is associated with it because it really depends on the human body's the age and also like if it's male, female, the mass, all of that. Back then, we had a different standard, but then NASA decided they don't want to go like with male, female, or the age kind of thing. So they switched to using the limit for the 35-year-old female for all the astronauts. But you think it's going to be more limiting. But it's not because they removed that 95% confidence level. That means they basically allow astronauts to be exposed to more radiation. But it also means the permissible mission durations has raised to values that are like, you can travel to Mars. So,
What?
questions?
Right.
I could finish. Oh my God.
So these interstellar neutral particles that are able to, charge exchange and come into the heliosphere, do those become important to any particle populations in the magnetosphere that we know?
Not really. First of all, they are neutrals. So they don't really interact with the plasma that much. But also, they're not really that abundant. They're very scarce. And they don't have much energy. We are talking about 20 kilometers per second to like 70, 50 kilometers per second. So they're not that energetic and they're very scarce.
So, Fatemeh, you've got two separate pieces of information from IBEX. First of all, you see the shift and peak of primary interstellar neutrals. In addition to the count rate being much higher in bin one, ESA bin one, the lower energy bin.
Yes.
Both of those things point to a higher radiation pressure than has been assumed in the past.
Yes.
So there's two things to that. First of all, why would the previous work on Lyman alpha be wrong, or why could we doubt it? And second of all, what's going on? What's the physics? Why is the radiation pressure higher?
The thing is, go back to those slides. We show that there's that 20%. Where is it? See. So we see there's a consistent 21-22% difference between the Lyman alpha observations and what we get for the hydrogen. So that consistency sort of tells us this is probably partially addressed by that difference. The radiation pressure has an order of 15% uncertainties as they have declared as their uncertainty for their observation. But in other works, like in Powell's 22 paper, they show that the same 20% is also there with the ionization rates. So it can really be the absolute calibration with the radiation parameter. But also this 20% really addresses a good part of the problem with the intensity of energy step one and two. But the problem that we can't really go through that type of analysis with this 20% is that, first of all, it partially addresses it, but also after the pack voltage change in 2012, we don't give any hydrogen rates for energy step two. That means we really can't do that ratio between energy step one and two type of analysis for hydrogen. It really can be the absolute calibration value for the value alpha observations. But it partially addresses the problem. We still need to very carefully observe our response function with to actually be able to address the problem.
So, Fatemeh, one of the cruxes is that we don't get the ISM hydrogen during the solar maximum, when the
Exactly.
radiation pressure is really the highest. So
Yeah.
those error bars are kind of
Very-
the limit.
Yes.
Can we make inroad in that with IMAP? As we are scanning what you said about the oxygen and
Exactly.
neon,
Yes.
that we apply similar to hydrogen and seeing it more
Exactly.
upwind.
Yes, IMAP actually addresses this problem or attacks this problem from all different aspects. First of all, we have the downwind and upwind observations. So that means a big difference in the ionization rates. So that's for one thing. But also we have higher statistics, better possibilities to observe hydrogen through solar maximum also. Looking at different directions, that means we have all different types of observations. Also a better known response function definitely will be helpful. So yes, with IMAP, we have a lot of hopes to address that problem.
To the other question of Nathan's, the root cause for the difference, can we then hope to give the Lyman alpha or EUV community a better calibration of their instruments, since there seem to be some open questions in terms of their absolute fluxes of.
Yes, sure. Oh, one thing that I forgot, like as another aspect is the separation. We have days with only hydrogen, so we can better address the retrieval problem with the hydrogen and helium. And then that means we can definitely better address this problem and make sure that what we find as the values for the radiation parameter will be much more reliable.
Any other question? Let's take this figure again.